Thank you very much for introduction. First of all, I thank the organizers for inviting me to give a talk in this wonderful online conference. I'm going to talk about some model of non-singular black holes based on these papers. Based on these recent papers. Okay, let us start. So we know that general relativity is the most successful theory, and there are many exact black hole solutions in general relativity. And in vacuum, so the Schwarzschild are Kerr black holes, and in the Einstein-Maxwell system, there are Reichenau-Norton black holes and Kerr-Newman's stationary black hole solutions. And even more, there is a black hole uniqueness theorem claiming that in the Einstein-Maxwell system, claiming that asymptotically flat stationary non-degenerate black hole is a Kerr-Newman black hole. And actually, in these black hole solutions, the curvature singularities inside black holes are quite generic. So this is a Penrose diagram of the Schwarzschild black hole, and so here is a curvature singularities inside the event horizon. And around the curvature singularities, the general relativity is no more justified because the step space-time is highly curved, and general relativity is no more cannot describe the space-time in such regions. And actually, there are several types of singularities. And the first type is a scalar polynomial curvature singularity. It is the best known one, around which the scalar curvature invariants, like the Kretschmann invariant, blow up. But there is another type of curvature singularity, which is the parallelly propagated or PP curvature singularity, around which the parallelly transported orthonormal basis components of the Riemann tensor, this guy, blow up along a curve. So consider a curve towards the singularity, and we consider the basis vectors parallelly propagated, and actually the component of the Riemann tensor, this guy blows up. And there are some examples which is not a scalar polynomial curvature singularity, but PP curvature singularity, like PP wave space-time or a three-dimensional Barger space-time. And the last type is a conical singularity, which is a quasi-regular singularity associated with peculiarities in the space-time topology. So by the identification in the flat space-time, we obtain a conical singularity, like the cone. And this conical singularity is not a curvature singularity in general, but it can be also a curvature singularity. And we know that the curvature blows up near the curvature singularities, and naturally thinking the quantum gravity effect should dominate around there. And then there is a belief in physics that a regular description of space-time must be possible in quantum gravity in some sense. So this is like quantum mechanics. The classical singularity of a hydrogen atom is regular in its wave function. But unfortunately, we still don't know the complete theory of quantum gravity now. Then, so we assume that non-singular black hole is realized in the low-energy classical theory of quantum gravity. This is actually a big assumption. And if such a theory exists, it must be a modified gravity, which could contain higher curvature terms or non-minimally coupled scalar field or etc. But the deviation from general relativity should be small in the far region from the black hole in asymptotically flat regions. And the central problem in this talk is what is a physically reasonable model of non-singular black holes? And in this context, the limiting curvature condition has been proposed by Frolov based on the earlier works in 80s, claiming that the curvature invariants are bounded in the parameter space of the solution. So it ensures that the singularity resolution is completed within that semi-classical theory. And if LCC is violated, even higher order correction terms are needed, or resolution is possible only in full quantum gravity. So for example, to clarify, so suppose that the space-time around the regular center is given by this metric. This is a de Sitter core. And the rich scalar near the regular center is given by this. And then the limiting curvature condition claims that this function lambda, this is the function of the parameters m and l, should not blow up in the parameter space. So this is a claim of the limiting curvature condition. And now let us see the first model of the non-singular black holes, which is a well-known Bardeen black holes. So the metric is given by this, with the metric function is this. And this contains two parameters, m and l. And m is actually the ADM mass, and the space-time is asymptotically flat. And this space-time reduces to the Schwarzschild if the length parameter is vanishing. And actually, there is a regular center. And the global structure of this non-singular black hole, Bardeen black hole, is similar to the rational Norton black hole, so like this. And in general, there are two horizons if the mass parameter is larger than the external value. And in this Bardeen black hole does not satisfy the limiting curvature condition because there is a parameter in the numerator. So if we consider the large mass limit, the metric function blows up. So it means that the curvature blows up indefinitely. And the parameter L, the length parameter, should be close to the Planck length if the generativity is modified by the quantum effect, a quantum gravity effect. Okay, so this is a prototype of all other non-singular black holes, the Bardeen black hole. And actually, until now, so there are many models have been proposed, and the situation is rather chaotic. And actually, many or most of them are not physically reasonable and may be discarded. And to do this, we use the effective energy momentum tensor defined by this simply. And this is actually useful to sort out realistic non-singular black hole spacetimes without specifying a theory. Because this effective energy momentum tensor should satisfy all the standard energy conditions, at least in asymptotically flat regions. And actually, in generativity, many fundamental properties of spacetimes have been proven under certain energy conditions. Okay, and here let us review the energy conditions. So the null and weak energy conditions claims that the observed energy density is non-negative for a null observer and the time-like observer. And the dominant energy condition claims that the energy flux does not propagate faster than the speed of light. And the strong energy condition claims that gravity is essentially attractive. And the violation of the strong energy condition is not so pathological in comparison with other three. For example, in the inflationary universe, the strong energy condition is violated. And this is the relation between these energy conditions. So if the null energy condition is violated, all other energy conditions are also violated. And if the dominant energy condition is satisfied, the weak energy condition and null energy condition are respected as well. But the strong energy condition is independent. And here I propose 7 criteria for realistic non-singular black holes. The first criteria, C1, claims that there is no non-coordinate singularities. So there is no singularities is allowed. But I also consider the weak version of C1, so claiming that only curvature singularities are absent. So the conical singularity is fine. And C2 claims that the closed causal curves are absent to solve the causality problem. And the C3 and C4 are related to the energy condition. The C3 claims that T mu satisfy the standard energy condition in asymptotically flat regions. And the C4 claims that energy conditions are satisfied on the event horizon of a large black hole. So in order for such a large black hole behaves like a GR black hole. And the C5 is actually the limiting curvature conditions. And C6 claims that such a space-time is realized as a solution for a set of non-zero measure in the parameter space of the solution. So this means that such a geometry is realized without a fine-tuning in a solution. So it is a generic, I mean that non-singular black holes are non-generic, the generic configuration. So this is a claim of C6. And the C7 is a dynamical stability. And among these 7, the first 5 are geometric ones. So we can examine these 5 criteria without specifying a theory. So we seek non-singular black holes geometries satisfying these 5. Okay. So in particular, we focus on asymptotically flat non-singular black holes with a regular center. So this is a big assumption. And we consider this metric so similar to the Bardeen black hole. And we assume the power law behavior of the mass function like this. And the regular center is allowed if this inequality is satisfied. And if P is vanishing, the regular center, around the regular center, space-time is locally ADS or the theta or ADS. And if P is positive, so the regular center is locally flat. And we are going to focus on the mass function with P is vanishing. This is similar to the Bardeen black hole in particular. And this metric ansatz gives effective energy momentum tensor in the form of the Hawking-Ellis type 1. So this is a form of T mu nu in the local Lorentz frame. And the relation between the energy density and the radial pressure is this one. So this is a particular equation state. And in this type of the matter field, the energy conditions are written like this. And the important fact is that, so there is a result by Demnikova that the dominant energy condition can be satisfied everywhere in this type of non-singular black hole space-times. So, but of course, there is the singularity theorem. So how we can avoid the singularity theorem? Let us see. So here is a claim of the Penrose's singularity theorem. So the space-time is null-geodesically incomplete under 3 assumptions. The first assumption is that the space-time is globally hyperbolic and admits a non-compact Cauchy surface S. And the second assumption is that the matter satisfies a null energy condition. And the last assumption is that the S contains a trapped surface. And this is the Bardeen black hole space-time. And let us consider the non-compact space-like hypersurface of S. And this shaded region is a future domain of dependence. And actually, this does not cover the whole future of S. And this is D plus S, and this doesn't cover the whole future. So this means that the Bardeen black hole spacetime is not globally hyperbolic. So it does not satisfy the assumption 1. So there is an assumption here. So this S is not a Cauchy surface, but just a partial Cauchy surface. So this is why the singularity theorem can be avoided, even under the non-singular black holes can be realized even under the dominant energy condition. And here I present some notable results. So the first one is that Dominic was 1, and the second is a strong energy condition must be violated near the regular center. And also the non-singular black hole is non-generic in general relativity. So this contains a matter field, which is a widely used class of nonlinear electromagnetic field as a special case. So let us see the last result. And actually, when we consider the general relativity with a type 1 matter field with a particular frequency of state, and then under an additional assumption, the general spherically symmetric spherically symmetric solution is given by this. This is a general solution, so the static solution. And here rho is a free function, and this m is an integration constant. And we observe that the space-time with non-zero m bar is singular at the center for any function of the energy density. So this means that non-singular black hole is non-generic in general relativity under these assumptions, because the fine-tuning is required. So it means that the generic non-singular black hole is successful only in modified gravity, not in general relativity. So this result contains this action. So this nonlinear electromagnetic field, this X is defined by this. So this action has been used by many authors to construct non-singular black hole solutions with a regular center. But actually, the general solution is given by this. So here, this is an electric constant and magnetic constant. And the FTR is determined by this algebraic equation. And this is a F function. And here is again the integration constant. And non-singular black hole requires a fine-tuning. M bar is vanishing. So the non-singular black hole is non-generic in this case also. Then we consider 4 different models of non-singular black holes with different mass functions. The first one is a Bardeen, second is a Hayward, and third one is a Dimnikova, and the last one is a Fan and One. So we consider these 4 different mass functions here in the metric function. And this is the 2-parameter family of solutions. And this M is an ADM, mass is a space-time is asymptotically flat. And the mass function behaves like this around the regular center. The space-time is de Sitter around there. And among these 4, only the Hayward black hole satisfies a limiting curvature condition, because there are m's in the numerator and denominators. So even in the large mass limit, the metric does not diverge and converges to de Sitter. So the limiting curvature condition is satisfied. And this is a graph to identify the location of the horizons for a given mass parameter for Bardeen, Dimnikova, and the Fan 1 black holes. So if you put the mass value like this, so there is one horizon and there is another horizon. So here is an inner horizon, here is an outer horizon. So if you put the mass value, this mx, so there is an extremal horizon located here. And if you set the mass lower than mx, there is no horizon. So the configurations are determined like this. So this is similar to the rational Nordstrom, but even in the sub-extremal case, it cannot be naked singularity, but self-gravitating regular soliton. And in the case of the Hayward black hole, the situation is a bit different because there appears a singularity in the negative mass region. So if you consider negative mass parameter, so there is a naked singularity here with a positive area radius. And generically, there are 2 horizons in the case of sub-extremal case. And let us see where are energy conditions respected. So let us focus on the black hole case. So these 4. So the black holes are realized under these inequalities. And then in the Bardeen case, null and weak energy conditions are satisfied everywhere, but the dominant energy condition is respected only in this region. And this is similar to the Hayward case. But in the Diminikova black hole and the Farman black hole, so dominant energy conditions is respected everywhere. And according to the Zaslavsky's result, the strong energy condition is violated around the regular center, like this. So this result shows that the Bardeen and Hayward black holes do not respect dominant energy condition at infinity, so it should be discarded as a realistic model. But the Diminikova and the Farman black holes are more preferable. So we are going to focus on these two non-singular black holes and rotating counterparts. To consider the rotating counterparts, so I assume one metric ansatz. So this metric ansatz was introduced by Gerses and Gersi back in '74. So this is the metric. This is like a Kerr space-time in the Boyer-Linkist coordinate, but m is not a constant, but a function. And then, so the effective energy momentum tensor is again the Hawking-Ellis type 1, satisfying the same relation between the energy density and the radial pressure. So I'm going to consider the same mass functions here in the metric. And in the Kerr case, in generativity, we know that there is a ring-like curvature and conical singularity at R is A with theta is pi over 2. So it's like this. And in the generativity, this is a curvature singularity. And the space-time can be extended beyond R is 0 inside the ring to the region with negative R. So we consider like this. So we go to the negative region of R. And then we again go like this, and we move like this, something like that, okay? And it is known that the closed time-like curves exist in the extended region with negative R. So there is a region of causality violation. But when we consider the region where this inequality is satisfied, so we can introduce the Duran coordinates in the GG space-time. So this is the Duran coordinates. So because this must be positive, because this is inside the square root. And there is a very nice property in this metric. So the inverse metric G0 is just -1, exactly. So this means that this one form, this T bar is a time coordinate, is everywhere time-like and hypersurface orthogonal. So it means that this coordinate T bar is actually a time function. So this is sufficient to prove that the space-time is stably causal by the proposition 4649 in the famous Hawking-Ellis textbook. And the stable causality means that there is no closed causal curves, and they do not appear even under the small perturbation of the space-time. So the stable causality is a stronger condition than the causal, just a causal behavior. So this means that if this inequality is satisfied everywhere, the maximally extended space-time is stably causal. So that there is no causality problem in the whole space-time. And let's see if the Kerr's ring singularity is regularized or not. So suppose this behavior near R is 0 with integer p in the GG metric. And there is a result by these two researchers that the ring is not a scalar polynomial curvature singularity, but it is still a conical singularity as Kerr. And also the null energy condition is violated near R is 0 if M0 is positive. And also similar to Kerr, the space-time can be extended beyond R is 0 inside the ring. So the space-time extension is similar. But still, it is not clear whether this ring is our PP scalar curvature singularity or not. And let us see what happens in the case of the rotating Diminikova and the Fan-1 black holes. So with this mass function, we can prove that the space-time is singularity free in the whole domain of R, except for the ring. And all the energy conditions are respected at space like infinity. And dominant energy condition is respected on and outside event horizon. And the space-time is stably causal because this is actually satisfied. And in the Fan-1 case with this metric function, because we see that there is a curvature singularity at R is minus L, which is a negative region of R, and the domain of R is given by this. And in this domain, the space-time is stably causal, and all the energy conditions are respected at spatial infinity. But because of this singular nature, this rotating Fan-1 black hole should be discarded as a realistic model of non-singular black holes. And here is a Penrose diagram of the rotating Diminikova black hole with a large mass. So here we are, and the dominant energy condition is satisfied here, and there is 4 non-degenerate killing horizons. So we go like this, and here is 1, 2, this is the inner horizon. And actually the space-time is symmetric with respect to R is 0. So we go like this, there is a horizon, and there is a horizon, and then we go to another asymptotically flat region. So, and in these blue regions, the weak energy condition is violated. Okay, but spatial infinity, all the standard energy conditions are respected. And in the extremal case, so there are 2 degenerate killing horizons, 1 and 2. Okay, and if the mass is smaller than the nx, so there is no horizon, and the space-time represents a wormhole like this. So let us see which is the best rotating non-singular black holes. So according to the 7 criteria, actually the 5, and this is a result. And according to the present results, among these 4, the Diminikova black hole is the most preferable, although it does not satisfy the limiting curvature condition. And still not clear that the ring is a PPC curvature singularity or not. And still there are several remaining problems. The first problem is, of course, to clarify the nature of the ring, if it is really a regular or curvature singularity. So to clarify if it is a PP singularity or not. And it is better if the Diminikova black hole can be modified to satisfy the limiting curvature condition, but in a non-ugly manner, of course. Or can we find other better models? And of course, so such non-singular black hole space-time should be a solution. So we should find a well-motivated theories which admit such non-singular black hole solutions. And also, because this class of non-singular black holes always have the inner horizon, so there appears a problem of the mass inflation. Because in general relativity, it is known that the rational non-rotation black hole suffers from the mass inflation instability. And at present, the different groups have obtained the opposite result for spherically symmetric non-singular black holes. So this problem has not been clarified yet. Okay. All right, so this is the last slide. So I want to show you, I want to give you some final take-home message, although you are already at home. But so first one is that you can find non-singular black holes in general relativity with this class of non-linear electromagnetic field, but they are always non-generic. Okay. And if you use a model, some models in astrophysics, so please check energy conditions at least at space like infinity, because all the standard energy conditions should be respected there in order to be a realistic model. And if the limiting curvature condition is violated, you need even higher order corrections or a full quantum gravity description to remove the singularity. And this is the history, but the rotating counterparts has been first introduced by Gersis and Gersi back in 1974. Okay, I should stop here. Thank you very much.